3 factorial x cubed. And then we start again, 0, 1, 0, minus, okay? So then what we end up with is the next one is going to be plus 0 over 4 factorial times x to the 4 plus 1 over 5 factorial times x to the 5 plus 0 over 6 factorial times x to the 6 minus 1 over 7 factorial times x to the 7 plus all the way through to infinity. And you can see that a lot of these terms are just going to drop off, yeah, the zeros, okay? The zeros are just going to drop off here. So 0 over 0, 0 factorial is effectively 1. 1 into 0 goes 0 times. So this actually goes to 0. So all of these particular terms here are just going to fall off. And what we're left with now is we're left with what looks like an alternating sequence. Okay, so this looks like f of x is now equal to 1 over 1 factorial times x, well, x to the 1, okay, minus 1 over 3 factorial times x to the 3, okay, plus 1 over 5 factorial times x to the 5, minus 1 over 7 factorial times x to the 7. And you can see the pattern. You can see actually what we have: 1, 3, 5, 7, and the next one's going to be 9, but it's going to be a plus. So it's going to be plus 1 over 9 factorial times x to the 9, because the exponent is the same as the input to the factorial, okay, minus 1 over 11 factorial times x to the 11, plus, and so on, all the way out to infinity. Okay? Now, what we can do is let's just keep an eye on this. What we can do is I suppose we could just leave this the way it is. Yeah, sure, I suppose we're nearly there. Yeah, okay? We could just leave this the way it is, or we could, let's say, we've expanded this out, okay, this particular summation. We could, let's say, pull it back in together, okay. You can see that if we want, we can rewrite this now as f of x is equal to the sum of, let's say, from n is equal to 0 to infinity, because it goes out to infinity, of, now, our numbers are going to alternate. So you can see the 1, 1, 1, 1, 1, 1. Okay, so the numerator here in relation to this particular fraction is always going to be 1, but it alternates between 1 and minus 1, 1 and minus 1, positive 1 and minus 1. And we know that if we consider, let's just say aside, okay, so if we consider, let's say, the sum from n is equal to 0 to infinity of, let's say, well, if we consider just 1 to the n, all this gives us is an infinite sequence of 1s. If we consider minus 1 to the n, you can see this actually starts off as minus 1 to the 0 gives us 1, minus 1 to the 1 gives us minus 1, minus 1 to the 2 gives us 1, minus 1, 1, minus 1. So actually this here would be an encoding, yeah, of the numerator, and it will capture all the signs. So actually this particular sequence, yeah, this particular series here is effectively from n is equal to 0 to infinity of minus 1 to the n, okay? But hang on, all over, let's just say all over some factorial amount. Well, look, these are all the odd numbers, yeah? So when we start off at n is equal to 0, okay, let's consider the odd numbers. So let's say to consider n is equal to 0 to infinity of 2n. Well, of 2n just gives, that's the even numbers. 2n plus 1 gives us the odd numbers. Isn't that right? Okay, that gives us, when n is 0, that gives us 1. When n is 1, that gives us 3, 5, 7, and so on. So actually, the factorial amounts over here are effectively 2n plus 1 factorial. And the powers of the x's, the exponents on the x's, so the x's are also to the power of 2n plus 1. Okay? So we could take this particular expansion and we could represent something like this. Yeah. Okay? So what we effectively have is that we have sine x, okay, is effectively equal to the infinite summation from n is equal to 0 to infinity of minus 1 to the n times x to the power of 2n plus 1 all over 2n plus 1 factorial. Okay? That's effectively what we have, okay, from the Maclaren series, yeah, representation of sine x. Okay? But we're interested in, okay? We are interested in sine x over x. Okay, but hang on. So f of x equals sine x over x is the same as, well, sine x from the Maclaren, from